Thanks all for coming this morning. I'm Jeremy Tanner, work at NVIDIA on accelerated Python. There's Andy, who will be joining me, going over community, which will be myself first, and then Andy to talk a bit more about ecosystem. What we got here? All right, and so there have been many Python projects in open source that take advantage of GPUs to go a little bit faster. And many of these were led by the community. So CUDA as a thing has been around for just about 20 years. And before those 20 years, Ian Buck, a progenitor of CUDA, made a program called Brook that stapled together, this is in the year 2000 or so, maybe 36 graphics cards to process across them. 10 years later, you have PyCUDA. Around 2012 or so, Numba comes along from our friends at Anaconda, at the time Continuum Analytics. CuPy from Preferred Networks. PyTorch comes out of Meta, helps you put together LLMs, make neat pictures of cute elves. Google makes JAX, Triton, and then as things pick up, there's Rapids for data science. Rapids is green because this is something that's come out of NVIDIA. All of the gray ones started by open source projects that have been started by the community. Warp for differentiable simulation has come out of NVIDIA, and CUDA Python, which we're on. Yes?
Quick question, what's the y-axis?
The y-axis, popularity over time of GPU compute. Thanks for the call out. That and it would get too long if all of them were stacked on the same timeline, and just trying to keep it spicy. So great ideas inside the company and plenty of great ideas outside the company. So community-wise, we're very much looking to work with y'all. And looks something like this. We will work with open source projects, many of them for scientific computing or doing Python a lot faster. In this case, scikit-image, looking through the issues and like, do you have plans for adding GPU or CUDA support? And oftentimes, open source maintainers are both overworked. That might not be their first job. There's probably lots of other things that the project is trying to get done. And so if we can help out and address some of the issues that we're uniquely suited to, we do. That ends up looking a lot like this. This is myself and many of the CUDA experts at SciPy, but we also come to PyCon and make ourselves available. And if there's questions, get those answered. Talk to open source community maintainers and then end users of projects, mostly to hear what y'all are looking to do and how that could be better or faster. Really enjoy conferences in the frame of PyCon because we start out with talks and then usually move on from the talks to open spaces where we can gather around tables and have some conversation. And then real magic usually happens towards the tail end of the conference. Since we've all come out here, we can sit down and do sprints. A lot of the best work happens more shoulder to shoulder than me up here and y'all out there. And so we're probably 5 days out from that at this point, but very much looking forward to it. Text is very tiny, but if you've not been to sprints, looks a lot like such. You will have a rundown of projects that different folks are working on, break into different parts of the room or convention center, and get down to work. It's a laptops open fun time. This gentleman looks very serious and knows quite a bit about both Python and GPU compute. But again, illustration of the shoulder-to-shoulder nature of the collaboration. If necessary, smaller sprints for a single project can be done. Image here is illustration for scikit-image. Stefan back there, who's started scikit-image, and sprinting and trying to add a GPU backend for it. And doesn't go quickly or immediately, but this PR says it's merged. Looks like that was started in August and finished around March, and so sometimes it takes a while. 184 conversation points or comments, 37 commits, but eventually we get there. The purple merged means good. Other places to support, because they help us collaborate, are some of our favorite foundations. So you're here. PyCon is put on by the Python Software Foundation. How many out there are supporting members of the PSF? Love y'all with your hands up. Love y'all with your hands down, but we gotta get those numbers up. Your homework for PyCon, or maybe today if you're on the Wi-Fi, is go to python.org and become a supporting member of the PSF. Having conferences like PyCon, where we can gather, collaborate, and learn from each other, is, I think, of utmost importance. And then that's not just here. The PSF is the fiscal sponsor and host of other regional Python conferences where we go, and I've very much enjoyed it, learned quite a bit. Also PyPI, which is doing, I think, 2 billion downloads a day. It's probably more now, but that was the last time I checked. Absolutely vital infrastructure that's used all of the time. NumFocus is the fiscal host of many of the fast Python projects. Their flagship is SciPy. That'll be going on in July. Would love to see you there if fast Python or scientific Python is your thing. And then the PyTorch Foundation. PyTorch takes excellent advantage of GPU compute. Their conference will be in October of this year in San Francisco. Also collaborate with some of your favorite companies, Python ecosystem-wise. Previously Continuum Analytics, now Anaconda. Their Jupyter and CUDA are available in Anaconda Cloud, and all of these projects that you see there, I think all of them are NumFocus projects, but Anaconda is a great way for you to get to them. There are also community organizations that we very much enjoy working with. This one in particular is a hackathon for GPU mode. Started as a Discord, YouTube channel, and GitHub. If you're looking to learn about various flavors of GPU compute, that is a great place to start. Other great places would be github.com, NVIDIA, and in particular, the Accelerated Computing Hub. If you give it a look, please open issues. Happy to accept PRs, and then if you see a guy who looks like me, certainly let me know what you think about that. I will pass off to Andy here, who will go over Python ecosystem.
Thanks, Jeremy. I'm going to have to apologize in advance. I did not expect such a small monitor, and there is code in some of these slides. But if you Google the title and go onto NVIDIA's online thing, you can get all these slides. So don't worry. You don't have to take pictures. If you need the slides afterwards, I can get them to you. So I joined NVIDIA September 2023, and I was told I have one job: make CUDA 100 times easier to use in Python. We recognize that using CUDA in any Python project adds a lot of complexity. And that's not intentional. We're not sitting there trying to say, oh, let's make your life more difficult. But we are trying to give you an exposure to the entire ecosystem. And doing that sometimes requires us to break a few things. And we're really working very hard to come back to the community and say, all right, yes, we realized that you produced a 3 gigabyte download on PyPI. Here, let us invent a new way for you to do this. And we've been working quite a bit with the community, and you'll see talks later in the week, such as Barry and Jonathan talking about our initiative to fix wheels and help the community use our software in a better way and so forth. And so, but what I'd like to talk about today is really like our commitment to Python and some of the stories that we've been able to enable over the last year. So this year we've announced that that Python is a first-class language in the CUDA ecosystem. First time in 20 years we've added a language. So C and C++ were our other main language. You can get, we do have a Fortran compiler, but it's not we consider it a niche language. We support it, but it doesn't support all of CUDA. Now, what does supporting all of CUDA actually mean? Well, CUDA is a full platform. It's not one piece. Like a lot of people think, oh, CUDA is just that like little thing in C++ that calls a kernel. That's just like one exposure, right? We go all the way down from the host runtime to frameworks and DSLs that make it easier to use. And for most Python folks, you're going to be just tickled to use the top level. And for some really, really deep thinkers who want to actually know every single bit that's hitting every single part of your code, we give you the ability to go all the way down to our runtime and everything straight from Python. Unfortunately, this means that there's quite a bit of libraries. And learning all those libraries, it becomes, we understand, that's difficult. That's probably beyond what most people want to actually deal with. But for a lot of folks, it also means that, hey, if I'm somebody who just works on communication libraries, I don't have to go learn PyTorch and all the abstractions of PyTorch. I can focus just on, for example, the MPI layer or shared memory layer. I can, if I want to work just on parallel algorithms like scans and sorts, and I want to get deep into like parallelism, massive parallelism, I can just work with our device libraries like CUDA Cooperative, which is cooperative threading and things like that. So I would think of this toolbox not as, oh, I have to learn all this, but as a way of like, if I want to modularize and use different pieces of the stack to get the maximum performance for my chips, we have it for you in Python. And if it doesn't work, it's a bug, and we'll file it and get it fixed. The other thing that's super important to CUDA is that everything's interoperable. One of the things we love about Python is Python really focuses on the composability of libraries and standards that can work together. And CUDA believes this pretty strongly. So we don't want to produce abstractions that can't work with other languages, and we don't want to produce code that doesn't interoperate, because at the end of the day, somebody's going to find something that breaks, and you're not going to be able to use your hardware very well. So this becomes like one of the challenges, like all those open source projects, which we love, often don't have perhaps maybe as much time or effort can go into fix every single bug. And so this is where, being a first-class language, now CUDA is put on the hook to say, yes, we will fix the bugs that come up from these interoperability and so forth. All right, so what does that mean for you? Okay, for a lot of folks, he's like, I start as a scientist, or I start as a web developer, or I start as a machine learning developer. I don't really need to know all the hardware details. And if you want to know more about like kernel programming, I invite you to go see Bryce Lobach's talk, I think on Saturday, and he will dive down into like how to cooperate threads and all that sort of thing, and like get very deep. And so there is a space for that, but let's talk about like your workflow to the CUDA ecosystem here. So the scientific journey, often something like this. You have, for example, this group out of Duke, Carnegie Mellon, University of Pittsburgh, Lawrence Berkeley National Lab, are all working to identify, they're going to identify supernovae on the Roman Space Telescope that's actually launching here. I don't know when it's launching, but it's soon. And so this is a very common pattern with scientists, is they're going to need to do some instruments. They're going to need to do that new instrumentation is going to come off of the machines, and they need to process it super fast. So scientists like Fortran. Fortran was nice. It gave you an array. It gave you nice syntax to go over that memory, and it maps straight to hardware. In Python, we have NumPy. It does this very similar thing. We have arrays. We understand directions and so forth. And we can write code in an array format. And Python's done really well at that array programming. So scientists, generally when we talk to scientists, they really love NumPy. They love this simplicity of the array protocols. But when you go to a domain library, like, well, now I have a whole bunch of different options, from symbolic mathematics to plotting to deep learning and learning algorithms. But underneath, because we have NumPy and it's the array that's bringing everyone together, we can actually interchange these codes. And that even goes to science, like more domain science codes, such as BioPython and quantum chemistry codes and so forth. And so, but it was this array system that allowed us to create domain libraries and then to actually do real science. And so we want to keep that same notion and that same idea of like, how do we get arrays? How do we get the things we like to work with that works with everything else? And so NVIDIA over the years have been participating in the Data APIs initiative that's been trying to define what these arrays equal in are about in other places. Like, for example, there's some talks on Arrow, and Arrow is a great one where we're going to share memory and give array interfaces shared memory access to other systems and so forth. A GPU is in the same vein where your array is now on a different piece of hardware than your CPU, but if I still have the array syntax, I'm able to utilize that and get my code over there for faster code. So like cuDF, if I'm giving a CuPy array, which is implementing this NumPy array syntax via the data array API, then I get all these wonderful libraries that do, for example, spatial computing or machine learning and so forth. And that's kind of our second bucket. And you can kind of see it going down the line. The data APIs teams have worked hard to like figure out how do we get arrays to be at every next level library and so forth. So we go to the GPU. We've figured out NumPy syntax, the arrays. We have CuPy, which was developed by Preferred Networks over the last decade or so, and it provides a really nice one-to-one mapping to NumPy arrays. One piece there, and oh man, you can't really read this slide, but there's a protocol called DLPack, which is an evolution of that came out of the data arrays, was an evolution of that array syntax, that array API. So if you look at NumPy underneath the C array interface, and it's pretty simple. It's basically just two structs. It's a buffer and some types. Well, once you go to deep learning and you want to be able to pass these things between distributed systems, between devices, and so on and so forth, we need a few more structs to like kind of pull it out. And this is how you get to a system that can actually be used on, GPUs from all ilks of GPUs. I mean, in here we have OpenCL, like the DL device type of OpenCL, Vulkan, Metal, Verilog, ROCm, and so on. And by working on a standard to bring a zero-copy GPU-aware data exchange, we're able to bring all these libraries to the same ecosystem. Now, CuPy will get you to an array-oriented computational method. And if you ever take a course on GPU computing, we end up focusing a lot on like what makes the GPU fast. After all, who's going to spend so much money on a device and not get its maximum performance? Because of that, we have over 80 Python libraries for all the scientific functions that we kind of use that are tuned by crack teams of PhDs who like love just looking at the PTX comes out and optimizing for every single architecture. We don't want you to have to do that. In fact, it's probably best if you don't do it because it's going to be slower. Even I don't do it. And I've been programming GPUs for a decade. That's the hard stuff. So we introduced NVMath Python, which is a library to give you that Pythonic interface to the highest performance libraries we have. So you don't have to know 80 libraries anymore. You don't have to know whether you're distributed. You don't have to know whether it's the sparse version or the dense version, the multi-process version, the MIG version, all these kind of options that you get with GPUs. You import NVMath Python, and we give you an API for peak performance. Now, this is not going to work on other vendors, like CuPy will, and we support DLPack, but you take that same vendor-neutral code and come use the accelerated code for our hardware. A few things that this provides, besides just a Pythonic interface, is just-in-time compilation and kernel fusion. So when you launch a code, for example, this code here will have multiple launches to an FFT. And so if you call that in the Python interpreter and it goes to the runtime 2 times, all of a sudden I get a double cost for an FFT planning. And for those who know FFT is an algorithm that has a broad butterfly network under it that actually requires some planning to actually coordinate all the threads super well. And so the standard is to go run a few cycles of just tuning jobs and then kind of plan out the sizes of those kernels, the sizes of the communication bits and everything else. But if I work in just the standard way, I'll have to do this planning several times. Whereas now with NVMath Python, we give you an interface using context and other things so that you can create a plan in your code and fuse through a single FFT phase and get a much faster piece of code. And so we provide this through stateless APIs that interoperate with popular Tensor libraries and frameworks and gives you that low-level Python bindings as well. And all available on Conda, pip, GitHub, and ready to use. So this is a common journey for us. And when we worked with the Roman Space Telescope, we helped them speed up their code by over 40x on a single node, where they're taking raw images of the sky and trying to find those very rare events. Is that? Oh, no. You're supposed to, well, I don't know. Sometimes on some screens you can see that down here, cycling through all the various images just so they get one little blip in the sky to find a supernova. And so by using NumPy, then going to CuPy for a single GPU, and then working with our optimized libraries, you're able to see massive improvements that can push science forward. So that's a very typical science story. The next kind of story I'd like to walk folks through is maybe with scaling. And so Dr. Quinn will be talking, I think, Saturday as well about her work trying to explore matter at the atomic scale. And so they have an X-ray that excites materials, and they need to plot out and find characteristics of that material on their LINAC coherent light source. And she'll give more of the story on Saturday, but you can imagine this X-ray, which is coming online, that produces terabytes of data, and they want to go to the next level, and they realize that you can't just solve this with one computer anymore. So in the same journey, NumPy gets you started. It gets you writing your algorithms, very prototyping, going to one node, maybe it's CuPy, maybe there's various other libraries you use, but this gets you to one node fairly well. And so then this is what happens to go to more nodes, because as I try to scale up and do more experiments, I got to process the data just as fast. Otherwise, I lose my beam time. So you try to find allocation on a supercomputer, such as Perlmutter here at NERSC, which has a lot of our GPUs in it, and I'm very proud to be there. And you read the traditional way of doing things, and it's, all right, go rewrite all your code with excellent libraries like MPI and SHMEM, and these are different parallelism models. So you have to rethink how your code is going to work, which is often a good approach for a lot of folks. But some of us don't have time to rewrite everything, so we're looking for something a little bit more implicit. And so this is where CuPy numeric comes in as an implicit parallelism model that requires that domain-specific kind of library approach that you're using NumPy and arrays and that sort of methodology, whereas MPI and vSchmim, we're passing around messages or verbs on a fabric. It's a different abstraction, so let's just stay in the array abstraction. So the way CuPy numeric provides a zero scaling or a zero code change scaling, so you can import it and get a lot of that array API functionality that we talked about earlier, and that will come pretty much right out of the box. Of course, you want to know what's happening under the hood, because who doesn't? And this is, okay. So there's two ways that CuPy numeric is built on top of, there's two ways we achieve the zero change scaling. One is, it's built on top of Legate, which is a runtime coming out of Stanford, this task-based system. And so there's the two ideas is that you have explicit parallelism that comes out of learning the graph from your computation and a unified data abstraction that you can compose these things. So if you have API, take for example, you have an API calls with some like adding, sorting, and calling various libraries. Those will be translated, so the libraries will be translated into tasks, and the Legate runtime will then schedule those tasks across the various runners that exist. And so this progression of like going from tasks becomes like you can place those tasks on any node, and the runtime just takes care of that for you. Under the hood as well, one of the biggest problems with explicit communication layer is that the communication doesn't know anything about where your data is. And so this is something that Arrow and other things have been trying to solve, and Legate provides its own store that takes the similar store to the Arrow concept, but also adds distributions and some first-class knowledge on where your bits are. So we're able to take a task graph and a representation of your data that can be represented in arrays or data frames or series and so forth, and that's kind of the underlying magic behind CuPy numeric. And to come hear the story about how we got their discovery down from, I don't know where the numbers came from, but something like it would take 3 years to do to under 5 minutes, and my understanding is they'll continue to improve this with CuPy numeric. Okay, so another journey we care a lot about, of course, is the machine learning journey. And machine learning journey has been pretty established at this point. PyTorch or JAX will bind to our lower level libraries like cuDNN, cuBLAS, and so forth, and this will go down our stack as needed. And you don't have to worry, like in most people who are like, I want to get on a GPU, well, install PyTorch and you get on a GPU and it's like magic, right? But underneath the hood, it's actually calling all these libraries. A trend that's happening right now is folks are saying, well, I want to get straight to the lower level so I can just write my inference code or something like that. And because it's built on a platform of CUDA, you can do that. You can go look at how and we work quite closely with PyTorch, and you look how they wrap all these codes and work on that each layer. But just because we have Python doesn't mean you can't get to the C+ and write your own. Now we're actually introducing a Python layer into cuDNN in order to give you even closer to that C++ level. And if you want to do, for example, a flash attention, here's a scaled dot product now from flash attention that you can now use both in inference and training, and either build this yourself, do something different. Like a lot of people want to change how their flash attention works. Try comes up with a new way of implementing flash attention, like seems every few years. So now you'd be able to grab that, put it into your inference code, and keep it in the same PyTorch pipeline using things like Lightning Thunder and so forth that speed up training. But the other thing that's super exciting with the machine learning community is their contribution to free threading. And so for folks that don't know, there's a global interpreter lock. So anytime I have a bunch of threads in Python, they actually get sequentialized and they happen one at a time, no matter how many threads I have or how many CPUs I have. And so for machine learning, often I want to do a whole bunch of stuff to get that matrix ready, to get the training job ready, and so forth. So we want to use all the threads we can. We've seen, so to this point, we've released a PyTorch Docker container that shows us being able to build data and build process images much faster using threads over processes. And the challenge with processes in this case is just when you're sharing a CUDA context, so like there's a context that controls what goes to the device, and that being shared becomes a bottleneck if you're using processes and you have to share that context through each one. Whereas with threads, we can actually get over that bottleneck and get every single one of those cores processing an image, pushing it to the GPU, and we see a pretty great scaling throughout our time using data, getting to feed the device with free threading builds. And if you want to play with our free threading system, there's a link there, and we're finding it to be quite nice. Yeah, and the Docker image, you can't see this picture, sorry, but we have over 80 libraries in the system, and we're patching the ones. We've added upstream patches to the ones that need some help. A lot of them are already working, and then there's a few that don't work, and they'll just drop down to a GIL mode if you end up in that code path. But we are managing, and hopefully we'll be releasing more free threading type things in the future. All right, I think, so one of the things that makes NVIDIA tick is that we started as a gaming company, and we really like graphics. So it's not an NVIDIA talk without something about graphics. Where it hits science is the simulation pieces. And a lot of our, oh no, what janky laptop do you give me here? Does it run? All right, well, you don't get to see those videos. But we're able to build, production grade quality, maybe not on this laptop, but so PowerPoint failed me. But if you go to the talk, oh no, there's a little button here. All right, so here's simulations that are the quality that you might get actually in production at a movie studio or elsewhere, all written in Python using these APIs and these community projects that we were talking about earlier. You can even see really fancy blueprints inside we have a product called NIMS, which is a microservice for NVIDIA's inference pieces, and like creating these things at a click of a button that produce really high quality visualizations and simulations for scientists to use. And then if you go to GTC, you can see this dog, the Boston Dynamics dog running this code. It's the same code that scientists might use to study like fluids or very simple setups, then transfers to robotic systems fairly quickly. Oh, here we go. But yeah, you go on GTC floor, they have this guy who walks around, and it's running Python. It's running Python to drive its GPUs to learn how to react to, in this case, these balls and so forth. All this is built on top of NVIDIA Warp. NVIDIA Warp provides geometric processing, such as meshes and point clouds and so forth, and differentiable simulations, just like PyTorch provided machine learning. It provided differentiation. We provide a similar model that has a auto differentiation interface that will give you the ability to simulate your whole code base. So things like your last Boltzmann kernels, which are really fast on GPUs, and how you can differentiate over them, and so on. There's quite a few methods that over the years that have been developed to work on GPUs and so forth. And then we also have like accelerated models for training, such as image processing and memory efficient cubnets and so forth. So this library is all just a pip install project, works on your CPU, works on your GPU, and it provides, the way it basically works, it provides a DSL that gives the author the ability to write a kernel, which is kind of like a CUDA kernel, but not exactly. It's a little bit simpler to write so that they can differentiate over it. and you're able to install Warp. There's, if you go to the Warp Lang GitHub, there's all these simulations inside, such as cloths and fluids and so forth, that you can run on your laptop today, all open source and able to be played with. So I encourage folks to go check out Warp. It's probably the easiest way to get to a differentiable simulation in our time today. All right. One last story to give is our story about is how hardware works. And so on the GPUs today, there's what you call streaming multiprocessors. They sometimes call them different things, but streaming multiprocessors that are effectively, if you think about old CPUs, they were very simple. They had nice pipelines, very few ACL units, and so forth. A GPU basically took those things and put them together so that there's a thread hierarchy, so you can call in blocks and warps and hierarchy to coordinate thousands of threads going to memory. And that was the SIMT. About, I don't know, within the last 8 years, we've been moving to what we call a Tensor core. And a Tensor core has an architecture that's not always well defined on each system, and people have struggled to use it because effectively you have to write PTX, so only like the most advanced codes used it. But essentially, it's the same idea, except you have multiple SMs together, and they have a coordinated structure for pulling in memory. So if you think about matrix multiply, whether you go row column or column major, you're going to blow out cache. So there's this whole methodology where they figured out how to swizzle into a diagonal system and be able to stream that through these SMs. Now, being able to actually program these things has been a challenge for even the most advanced programmers. And we're announcing a new programming language that gives you access directly to a Tensor core so that you can load more memory and actually work at the tile or block level as opposed to the thread level. So just like with CUPy numeric, we took arrays, we made it implicit. Now we're going to give you blocks instead of individual threads, individual elements of an array, and give you the same interface that now the Tensor core can actually speed up. So the programming model is designed to be very Pythonic. Here's an example of a soft max just written in NumPy with just array syntax, doing like max, expiration, exponentiation, sums, and so forth. And all we do is take that same thing, add our tile compiler, so these CT at func, that'll take that piece of code and turn it into PTX code that can then be loaded onto our devices. And you just have to load which tile. So now you're loading in and out, but you keep the same NumPy code. Pretty much the same NumPy code is going to work and be more efficient, be able to hit our Tensor cores at the same level. These operations are cooperative, so you don't have to worry about threads knowing which is shared and which is shared memory, which is global memory. It simplifies all the GPU thread handling for you, so you don't have to go read the PMPP books to understand how all different thread models work. This is coming out, I believe, later this year. It's being recorded, so I don't want to say a date because somebody will hold me to it. But we've announced it at GTC, and we're working with partners to expose this to all the different mathematical libraries we have and give to the Python community. Here's an example of a numba kernel written for matrix multiply, and the same code in QTile. We're using this tile-based system. Block-based programming has been a evolution in the academic space. Linear algebra world has been playing with this for many, many years, and this is how they get top speed. Now you don't have to go learn all the different techniques. You can write pretty much this very similar code and handle all your different matrix multiply variations in a high-level language. We will be releasing Implementation, Llama 3. Llama 3 was relevant when we wrote this slide. I'm sure Llama 4 will produce as well, but that's we do have a Llama 3 experience. And the thing here is like, so if we look at Qtile and we look at Torch, today, like Qtile is a very new model, hasn't been really optimized on new chips and so forth, and it's getting pretty much 93% of the end-to-end peak. So we're already seeing really good performance with a new abstract model to give you Tensor Core performance. And so this is something coming that we just keep working with, work with the community, find new applications to speed up in a higher level kernel language, if you will. So lower effort, fewer lines of code, shorter time to implement. We're hoping this becomes something that helps everybody get on a GPU faster and so forth. All right, with that said, those are the journeys I had for you today. If you want one thing to do, one place to start to learn how to use your GPUs and program at every level, the Accelerated Computing Hub is an open resource. It's liberally licensed and ready for any contributions, any bugs. Feel free to go on, and there'll be, I believe, later this week at sprints and so forth, we'll actually have some codes to get you a GPU if you want to play around with it. I think we'll be at the sprints, is that right? Yeah, so we'll be at the sprints. If you check it out, come find us and we can get you on our cloud system that can let you actually learn this piece of this new paradigm of computing. All right, with that, I'll end here and take any questions you might have. You're welcome to either come to the mic or I can just repeat it. So.
I can also run the mic in your direction if that's...
Yeah, go ahead.
Qtile going to be open source?
The question is Qtile going to be open source? So the compiler that I just showed you will be open source. That will go to a compiler to a system called TileIR, which is an MLIR dialect, which we are working with the MLIR community to see how to push that to a dialect. That's a process. There's a community around MLIR that we're working with, and that'll be open source. Now the translation from that to our device, that's not going to be open source, but it's not really going to be. People ask me all the time, why isn't X open source? And often it's just because you don't want to know which hardware wire goes to which part of the memory, and we'll take care of that for you. But it will be, the compiler will be available as open source, and the IR that actually underneath that the MLIR world uses will be hopefully upstreamed. But we got to work with that community to figure that one out.
Awesome. Progress.
Thank you. There's another question?
So how is that journey supported by some of the libraries that you mentioned?
Thank you very much. The question was, how do we support folks who are on laptops and that need to move to a cluster rather than folks who have to work on a cluster all the time but don't have access to a GPU? Perhaps they want to use Metal or some other accelerator on a Mac, and how is that supported? Unfortunately, we don't support Metal, but most of the libraries I talked about today are all CPU supported. So NVIDIA does have ARM chips, and we have, I know that the ARM, the Python ARM person's here, so you can put complaints to Python on ARM there. But we do work with ARM, and so we do accelerate CPU codes. NVMath Python, which I showed, will even use MKL if you're on an x86 chip, and so it's trying to make the best choice for you. Now, NVIDIA is the expert at making our GPUs the fastest, so we're going to obviously prefer you to come to our GPUs, but we do provide, and the way I kind of put it is we'll give you best of class performance on the CPUs that you have, and we will use open standards so other vendors can give you speed of light performance or top performance, but if you want state-of-the-art performance, our hardware is going to get you there. So hopefully that's enough. Any specific questions about how to get those things to run? Happy to take them.
Rose at all. Brev's also an option for like notebook for GPU by the minute.
Yeah, so we purchased a company called brev.dev, which is kind of, I think they sold themselves as the Google collaboratory for pros. And so brev.dev, you go and you can get a GPU pretty quickly. And then with VS Code these days, you can actually work with it almost like it's on your laptop. So there are cheap options to get a GPU. And we're constantly working with Google Collaboratory to make sure that they have the latest software installed. Fortunately, it's not as easy to update the software on Google Collaboratory. So if you want like your own specific software in a Google Collaboratory environment, you look at, is it
NVIDIA notebooks.
NVIDIA notebooks, or if you look at brev.dev is the old site, and it takes you to a notebook. But for a lot of folks, Google Collaboratory is just so easy. You press a button and get started. But if you have a specific software set, we can help you get it on the cloud too. Jonathan is telling us that Hugging Face announced the GPU cloud. I don't have any information on that. If you want to, okay. So there's Hugging Face GPU cloud, same as Google Colab as promised by Jonathan. Go bug him. Any other questions? In the back. Yeah, how to find these slides. Can I browse and try to find them?
Is there anything dangerous on there?
Okay. I'm touching another person's laptop, it's just, so if I say.
The world's riskiest clicks.
What's the name of the talk? Accelerated Python GTC.
If you look for community ecosystem, it'll probably jump there.
It's the same title as this session, and ecosystem. Okay, so you get to this page here, and all right, well, it's supposed to be, that didn't work. All right, so yeah, so it's the same, so the NVIDIA GTC session catalog, and you come here to this talk, and if you log in, there'll be a download button. So they want to collect your email address and that sort of thing for all their analytics. And if you don't want to do that and you have a thumb drive, I can give it to you here. Yeah.
I had a question on, and I don't know if you know it, but how hard was the pre-threaded data loader in PyTorch to implement? I'm basically thinking of what if I wanted to do that in another framework like PyData.
Yeah, so the question is, how hard is it to use the free-threaded Python to implement the data loader in Python? And I would definitely have to punt on that. I can take it to our engineers. It didn't seem, my understanding is it's not super difficult. It's more difficult to get the free-threaded build than it is to like change the data loader code. But that team, they work on that data loading every day, so it's a little hard to say how hard it would be for you to port that. So, but if you go to the blog post that was mentioned and and there's a Docker image, like that has all the builds that you need to get started. Yeah, and ask Sam. Sam's speaking later today, so maybe even in this room. I don't know. Question.
Hi, thank you. Great talk. I was just wondering, do you know of any use cases for Warp on microscale physics like protein modeling or other kinds of things that need to consider non-electrostatic forces, for example?
No, but we should definitely chat. That team, is any Warp team members here today?
I don't believe it.
Yeah, I think they weren't able to make it out this week, but they do quite a few collaborations with universities and academics. So that would be something that we'd love to chat about, but I don't have like this one right off the bat. Yeah, any other questions? Shall we get coffee? Yes.
How much is the CUDA Python framework hiding things like, or abstracting, like copying memory from device to host and all,
How do I get back to the slides?
different kind of pointers and all that? That abstracting all that, is it still
Yep. So
C++ basically, but Python?
is there, can I get to the slides? Slides, sure. So the question is, how much is CUDA Python hiding things like memory copies and pointers and so on and so forth? And so that slide I showed with like all the different levels. So basically, the lower you go, the closer you get to those things. So for example, we have CUDA.bindings, which is effectively just a generated interface from the low-level CUDA piece. So it's basically a one-to-one matching from our driver API to a Python interface. That interface is very hard to use. If you want to like commiserate memory, Brad's over there. He's used it all the time, and he can tell you about every single problem that comes out. He also runs a system called Rapids Memory Manager. And Rapids Memory Manager allows you to interface with those lower levels so that you can control how that memory gets allocated and how it may be pinned or moved, or there's a whole bunch of different allocation systems. And just like if you kind of keep up with core Python, they've changed a lot of their memory allocations. The same thing in CUDA land. We have different ways of allocating memory and that sort of thing. So you can control that through a lot of things Brad has built. Now, most people don't want that joy. So if you're using something like CuPy and you say print, for example, then it's going to automatically pull things over for you and so on and so forth. The biggest complaint I get about CuPy numeric is like it's the same idea. Like you say print, well, guess what? If my memory is across the entire cluster, I just moving a terabyte into trying to, like a print statement might try to move a terabyte to a single node. So some abstractions have to change because of the fact that like even if I do try to do whatever the compilers or the program's trying to tell you to do, it's not possible because I don't have enough memory perhaps, or it'll be really slow. So the way to kind of say it is because we're putting it was this one. I gotta click. Okay. So at the lowest level, the host time. So we have CUDA.bindings, which is auto-generated. It's going to deal with pointers and so forth. We have a new thing called CUDA.core, which is a object layer on top of the bindings, which gives you full programmatic access to all of the CUDA runtimes that you might see in C++, but they're in Python. So you don't have to have a separate tool chain to run your compilation. It'll take like numba outputs. Other libraries, like device libraries, often are in different formats, like Kubin, PTX, and a thing we call LTOIR, which is link time optimization. So it's like basically a relocatable kernel thing that can be fused. You can give it to the driver and it can fuse it on the device and so forth, and all that in CUDA.core. And you can kind of see that's still an evolving interface, but that's like the evolution so that you can get to any one of the various interfaces that make these libraries go fast and put those together. And on top of that is the compiler stack. So we have numba, we have an IR. We're working with the numba team a lot to make that IR CUDA friendly and expose all of CUDA. And that's all open source, and you can find numba CUDA working there to actually get to those lower levels, and we patch it together at the host time through CUDA core and so forth. And then NVJIT that just is the thing that like takes LTOI. So if I have two libraries that are going to link later, NVJIT will link them. So it's not C++ anymore. It's all going straight to IRs and compiler intermediate representations, and they get linked. So you pass it to the driver, and they get linked at runtime typically. They can be cached, and there's other advanced things we can do. But it's no longer just use the C++ interface. In fact, so much of CUDA is being JITted these days that even the Python interfaces are going to be faster in the future because Python's a better JITting system than C++. So that's a constant debate for us. Like, why we release Qtile on Python first, because it actually fits the Python ecosystem better, because everything's going to be JITted. You have to know a lot about the execution environment to cooperate with all those threads, and Python gives us those higher level abstractions to work with. Sure thing. Anybody else? All right, thank you so much for your time and patience. Enjoy the coffee.